Hi, I'm Edilmo Palencia, and in today's talk, I'm gonna be talking about machine teaching, which is a new service that we are trying to create here at Microsoft. So the agenda for today's talk is gonna be trying to describe what we are trying to achieve, how RLlib and Ray are helping us to actually achieve that. In today's industry, we have a lot of automation already taking care of a lot of work, but also we have a lot of complexity. And this complexity imposes a lot of challenges that are forcing the industry to look into intelligence as something that could help to move forward. Intelligence could take many forms, and today you can see basically three forms that is described in this picture. So you have connected systems that are sending data for people to observe what is happening. You have predictive approaches where systems are taking those points of data and trying to perform predictions about what could be happening. But even you can try something more advanced and take those predictions and data and try to make optimized decisions that try to outperform in terms of a goal or any other business need that you could have. But today there are a lot of limitations in achieving that. In autonomous systems, it's about working in the last part of this spectrum where we focus on predictions, or even beyond of that, trying to create systems that could adapt to the changes in the situation, which is the main challenge in today's complexity. Or you can go even further and make those optimized decisions, try to move the business towards a goal that actually could create new opportunities. Here we present what we have seen so far with this graph from Gartner. So far we have identified that the best outcome is coming from having humans involved in the process. So that could be a system approach where machines and humans are working together to optimize towards a goal. Or you can have fully autonomous system making decisions independently, but still the humans involved in the process of creating those advanced systems. Our value proposition is about something that we call machine teaching, which is a way to get knowledge from subject matter experts and put that in machine learning algorithms that are also combining optimization and control strategies that have been successful so far for autonomous things. The solution is about building, training, and deploying something that we call brains. And those brains are high-level models that are able to generate actions that are optimized and can control situations. Those brains are built by combining different machine learning techniques like reinforcement learning and also incorporating new machine teaching approaches that we are creating. This autonomous system solution already has a tool chain that starts from providing tools to inject the knowledge from the experts into the system. We also have advanced tools to create simulations in scale and advanced simulations that could speed up the training process of these complex systems. We also have what we call the AI engine, which is in charge of taking all this input, and connected to these advanced simulators and creating the brain and training the brain that you want at the end. And this is the last part, you will use to deploy this advanced piece of machine learning system. So we also provide a workflow for development. And the workflow starts with a program, a machine teaching program that you can create using a special purpose language that we developed that we call England. After that, you can create or customize a simulator in your end and connect that to our system. So, and at that point, you're going to be interacting with the AI engine and the service around it to train the brain. After you have the brain ready, you're going to be able to use our service also to deploy that to the real world. For machine teaching, reinforcement learning is key. But in order to achieve what we want around autonomous systems, reinforcement learning is not going to be enough. So it's important for us to be able to combine different approaches to reinforcement learning or related to reinforcement learning, but not exactly equal. And something like representation learning, imitation learning, transfer learning, memory approaches are things that we are combining and using in the machine teaching approach. So it's very important for us to have a reinforcement learning library that is extensible and flexible. And that's why we are looking to the open source community and try to do not build something from scratch. Because we foresee a future where reinforcement learning libraries are going to be well established and smoothly integrated with distributed computing systems. So today we think reinforcement learning libraries are in the early stage, but we are sure that we are going to overcome that and get something very stable that everybody can just use in the enterprise. RLlib is our bet for reinforcement learning. We think that RLlib is succeeding in making something hard as reinforcement learning easy. It's comprehensive. You are going to find a good set of algorithms and things related to that. It's extensible. So far has been possible for us to extend or customize different parts of the reinforcement learning development, like algorithms, metrics, models, and things like that. And it's also flexible in the sense that we are able to use it RLlib as it is for experiments, for proof of concept, and also in production. It's also important for us that the library, in this case RLlib, is something that we can use without too much constraints about what else we are putting into the picture, into the system. So be able to keep separate concerns wherever we want. And if we want to move away or move closer to RLlib, we should be able to do it, and we are able to do it. We are also able to go beyond reinforcement learning without RLlib interfering in those decisions. In the long term, we expect that RLlib could stabilize the API to make stronger guarantees to enterprises about not breaking backward compatibility, and that is the only pain point that we have having so far, but we have seen a lot of improvement in that regard lately. Distributed training is other key part for us, and it's not only because of reinforcement learning. Machine teaching requirements imply simulation, and simulation is something that brings a lot of undeterminism in the process. The program that the expert is authoring in England is also yielding a lot of dynamisms in the sense that you could have computations that you don't know in advance because those computations depends on other computations. So it's very important for us to be able to code and create this machine teaching system with a dynamic approach. And it's also very important for us that we can be in an environment of execution that is scheduling tasks just in time. So as soon as the task is declared in the program, that should be running and put it to run in wherever place in a cluster where the resources are available. So Ray is our framework for distributed training in general. So it's not only about RLlib, it's about being able to train something advanced in a distributed fashion. And for us, it's very important to have something like Ray that we can use with Kubernetes in a microservice architecture like the one that we have, and be able to do that just for training without interfering with any other piece. So the fact that Ray is AI focused is very important for us. So here we have a demo, and I'm gonna switch my screen to show that demo. In this demo, we are showing, first of all, this device. So this is a device, actually a hardware that we developed especially for machine teaching. So it's intended for practitioners get their hands dirty playing with something real, but at the same time learn how to use our tool. So, and you can see that we already have a simulator, and you can see different metrics about the simulation. Here, for example, here we are seeing the velocities of the ball, and we are seeing the obstacle distance and the obstacle direction. So the obstacle is this red point, it's simulated with this red point. And what we are gonna try to teach here is the hardware, how to keep the ball balanced in the center and do not hit this obstacle. So it's gonna try to avoid falling out of the plate, hit this obstacle while keeping the ball in the middle. So you can see in the UI that it's showing how many simulators are connected. We are gonna see overall metrics. I'm gonna explain this one, and which is this same that is shown here, which is called goal satisfaction. I'm gonna explain that later. You can also look at the rewards. So here we can see the rewards so far. We can see exploration and also the evaluation of the test performed over the policies that you are getting. So let's switch to the teach part. So here the teach part is where you can author your in-link program. So as we said before, you are able to express your expertise about the subject. And the constructs are the following. So first of all, we have the graph. So the graph is a set of concepts and their relations. So, and the concept is representing a subject or idea that you want the AI to learn. Inside the concept, you have the curriculum, and the curriculum is expressing how the concept should be learned. Inside the curriculum, you have different components, and the main ones are this one, goal. So in this case, we are using goal instead of reward as a concept, not as a concept, as a way to say how you succeed in learning this concept. So here, the goal is trying to keep the ball in the center without hitting the obstacle. So the way to express that is you can declare different sub-goals, in this case, avoiding fall out of the plate, and you express that with using the state that you declare above, so the state of the system. And you can also put in another sub-goal, which is driving to the center. So, and again, in terms of the state. And last but not least, you also specify the sub-goal of avoiding the obstacle. So, and after that, you can go further and express how exactly we could learn that concept in a staging way. So lessons is a way to stage the process of teaching, and you can have multiple, but at this point we have just one, and we are using that lesson to express the different kind of balls that you could be expecting in the plate. So here we are randomizing the radius of the ball across the different episodes of the training. So as you can see, you are declaring what you want to teach and you are not actually coding anything special beyond just expressing some structures, like for example, the state, and you can differentiate the full simulation state from the actual state that the system is going to observe. You express the action and you express the configurations, so the context. Here you can put details about the context. In this case, we have here the initial velocity, initial positions, and also the characteristics of the ball. So switching back to the train, so showing the goal here, we can see that actually the overall goal is being tracked with this goal satisfaction metric, but also we can track the specific sub-goals that we declare, and we can see how good we are doing in those three sub-goals. And if you feel more comfortable, think in terms of reward, so you actually can see how is the system doing reward-wise. And in this case, the reward function was crafted by the AI engine based on the goal that you described. So besides that, you are also able to stop the training, or the training could stop automatically if it's doing good enough, but you can stop at any time. And when you stop, you can actually assess the policies that you're getting. So like with the same simulator, but here you can like test out the system, the brain, just to make sure that everything's good. And actually you can export the brain. In this case, you can export it, like, for example, a Docker container, and deploy that in somewhere. So in the case of Moab, you actually can get the container deployed back to the hardware and test your system. Here you can integrate your own simulators, and you can create as many brains experiments as you want. And whenever you change something in the England, different versions of the brain are created. So yeah, we have many features. You can use this to go from the overall description of the system and the training process, and map that directly to the piece of code that you are interested. So you can see, for example, where the actions are being taken, and then take it from here, and you can go directly to the structure, define the actions, and things like that. So that is the demo that we have for today. So in summary, in today's talk, we are describing how Ray and RLlib are our bet for reinforcement learning and distributed training. We are betting on RLlib because we are seeing great progress towards being a well-established reinforcement learning library. We expect more stability in the API, and we are sure that that is going to be happening soon. And in the future, we see very important for RLlib to get better design patterns applied in the development process in order to provide more extensibility. We foresee extensibility as a key factor for our reinforcement learning library. We are betting in Ray because we are seeing great progress, not only in features, but also in fixes around this very complex system. We expect improvements in lifecycle management, and for sure, we are sure that that is going to happen soon. In the future, we would like to see a much deep integration with Kubernetes. For us, RLlib is at the core of the AI engine. Ray is at the core of the infrastructure supporting that engine, which is making training. And Kubernetes is our orchestration engine for the whole workload of our solution. So that is the summary of our presentation. In next slide, I want to just show a quick video of this is the real hardware of Moab. And what I'm gonna show you is a very short video where with the brain deploying this hardware, and the brain is trying to learn to catch balls. So let's take a look. Yep, so that's it. This looks simple, but actually was quite hard to achieve. So the ball could be coming from anywhere, and the hardware is going to try to catch it. So that's it. That's it for today's talk. And thank you very much. I'm happy to take questions now.